Let V as vector space on real field in math, then the convexity inside the V vector space define as for all x and y inside the vector space, there is lambda which element of this closed interval such that this thing inside the vector space, or we can modify as this blue, which here we mean to any point between x and y, or in geometric means all point between x and y is the element of vector space V. And notice that V here can be a subspace of vector space, so as long as vector space, the convexity is about this. Next, we let f that map V vector space to real number set. Then f is a convex function if satisfy this property, and f is concave if f satisfy this property. Then we can remove equality to make the strictly convex or strictly concave. In the same scenarios, and letting f is differentiable function, we will have these such as f is convex, the first derivative of f is monotonically increased, and the second derivative greater or equals to 0 is equivalent statement. First, let's start prove C consequence to P. Let the second derivative of f greater or equals to 0. Here, we can see that the first derivative is monotonically increased. Why? If we take the first fundamental theorem of calculus by this equation, we see that the inside of this integrand is greater or equals to 0 as our first statement. Then, if x is greater than y, the integration will make sure the result is positive. So here, the gradient in y is smaller or equal to gradient in x, which means that the statement first derivative of f is monotonically increased is true. Next, we prove that P has consequence to A. Let the monotonically increased property such as this when x greater than y. As you can see that f is differentiable function. Then we can let z be equals to this, which z is some kind in geometric means is a point between x and y. So by first derivative monotonically increased property, we will have this inequality. So if we take the integration for these three, we will get the result as this, which the middle term here come from fundamental theorem of calculus. Next, we separate the inequality, so we will have this two inequality, and for above, we switch the sign, so we have this, which by next modification, like multiplying, then we adding these two inequality, we will have the result as this, which by simplification, we will get the result as this. Inside this box parenthesis, we will get the form as this, which by simplification, we get the another result that this parenthesis collapse to 0, so this term will collapse to 0, and then finally, we can substitute original of z, so this inequality will return to the definition of convexity. So the P statement will consequence to A statement. And the last one, we prove that A has consequence to C, which by letting f as a convex function, taking lambda is about 1/2 and y equals to x plus h. So by convexity definition, we will have this inequality, and by some modification, we will have this inequality, and because this is a differentiable function, we can take h approach to 0, so we can have the second derivative definition by using the fundamental definition of derivative. So back to the statement before, we will get this tree statement is equivalent.